Okay, so today and on Monday, we may not get it all done today. Want to get the Schwarzchild metric. So in order to understand the Schwarzchild metric, you're going to need to do homework for. Because it turns out that on the very back of this, there are the Ricci tensors for this problem. And we're going to use these to actually then derive the metric, the Schwarzschild metric. And so I'm going to use some results today from here. But I want to set up these ideas because they're not necessarily always the most obvious points. And once we get the Schwarzschild metric, we're going to get a lot of mileage out of it. Because many of the applications we're going to do will do that. We'll see how we can deflect starlight. We're going to see how we get the recession of the perihelion and Mercury. We're going to get our black holes from that. Gravitational time dilation, all the really cool stuff, including we'll get to the we'll look at actually what it means to be a wormhole too, because this is also going to contain a wormhole solution. With a really disappointing, physics in there in the sense of you can't go through it. It's going to close up on you as you get closer to it. It closes up on you. And it's really remarkably disappointing because here you have a perfect wormhole. Okay, you probably die in the process of getting. But if you didn't, you have a beautiful wormhole and you can't get through it. It's one of the ironies of life. Okay, so we're going to need a result here. So we need some recall. What recall? Before we derive the Schwarzschild, and do I have, I think we'll go up down to them. Really? Okay. Schwarzschild. I think it's like that. Okay, before we derive the Schwarzschild metric, we need to recall some results from Wednesday. Okay, so remember we had G mu nu. We said this was for a weak gravitational field. And that's still on the board. That is. Okay, what did we say this for a weak gravitational field? That's two terms. Eta mu nu. Excellent. Eta mu nu. Okay. That's our weak, that's the flat space time metric. And then what did we add to that? A small correction, which we called H. Now we worked out H00. H00 was 2 phi over c squared. Right? So that means really, what is in G00? Frequently called the goo term. That would be eta 00. It's H00. So eta 00 is -1. And this is what? This is minus 2 phi over Cm. So this is minus 1 plus 2 phi over Cm. Where? What did we say phi was? Minus G M over R. Excellent. That's correct. Good. Okay. So you can put that in here. And so this is really minus this is minus 1 minus G M over R. Use a 2 here. And there's a c squared there like that. That is our g00 term. So I'm going to put that all over here. So I'll say g00. It's minus 1 minus 2g then rc squared. Okay, we need that. Okay. That's going to allow us to finish this. So let's go on and do our get to our method for the Schwarzchild. Okay. This is the first problem that was solved in general to be first metric. Okay, so recall the Einstein equations. What are they again? Let's start off with G. G mu nu equals
1/2
8 pi G over c to the fourth, excellent. Okay, times T mu nu. Okay, and I think with 1/2 is coming in here. The G mu nu, okay, there is a half here.
times the gradient of R, or the covariant derivative of R, or just R.
R times G mu nu. What goes in front?
R mu nu minus
R mu nu. Read this. Now, if I'm off, now this capital R we could write in terms of t. What did we do? We multiplied both sides by g, little g, upper mu nu. So we did this. What does that give us?
scalar
So, well, this times this is,
scalar R.
now that gives us R mu. Or it also gives R nu. Doesn't matter which one you do it. Minus a half R. What is G mu nu, G mu nu?
That's
Fingers right there.
delta
Kronecker delta.
mu or mu either
Mu or nu. I'll keep it in use there. Equals 8 pi G c to the fourth. Okay. Ooh, yell at me. Yell at me. This guy here? Oh, he is there. Never mind. Don't yell at me. I put that wrong one. I thought I had a big bracket. This guy then is mu, which is going to come t. Okay, so this is what this is our
curvature scalar.
yeah, this is a curvature scalar. This is just R. So this is R minus a half times R. Now what is delta mu mu? Or is it 4? 4.
Oh, right.
Because
You're summing.
you're summing. So delta when they're the same as 1, but you're summing of these, so it's 4. It's t. So this is minus R equals 8 pi G c to the fourth t, where this R is this guy here. So another way of writing the Einstein equations are going to be this. I mu nu equals 8 pi G c to the fourth T mu nu. And then if I take that over here. Okay, you should yell at me here. Don't yell at me here, but yell at me here.
There's no side. I can see.
You know, I said there. If I put that in there, that's doing a positive, that goes to a 4. I'll take this back over here. And this is gonna be 4 pi g t c to the 4th, c to the 4th. G mu nu. Okay, that makes sense. So we have that. So let's look at vacuum solutions. So what would be T mu nu for a vacuum solution? This is as stupid as you think it's gonna be.
Either 1 or 0.
One of those is correct.
0.
0, because there's nothing there, it's a vacuum. So it has to be 0. So what we want to do is solve this. So we need to solve. Okay. And what would we guess from that? If we had a vacuum solution, what kind of symmetry do you think we'd have? Oh, spherical symmetry. You'd expect that. But at some point here, we'll say we're going to have some origin here. And we'd expect the problem to be spherically symmetric there. And would it depend on time? No, you'd expect a static solution. So the problem would be spherically symmetric. And time independent, meaning the metric. And you don't say time independent, usually in relativity, you always refer to that as being static. Okay, so that means all the little g mu nu's can't depend on time. So that means the g mu nu here, this really, this right here, this has to equal 0. I'll call it cell phone. If, let's say 4 x 0. In other words, g mu nu has no time limits. That makes sense? So what we want to do is I want to write kind of a spherical problem and make it more general. So let's write the general ds mu metric that is static. It's spherical. So let's start off by writing I needed that. So recall that the flat space symmetric. This. Let's see. Damn it. C might, okay, we might use Roger units where C is sometimes 1, sometimes it ain't. Okay, in the same equation. Okay, we might be, I think what I. Okay, I copied it from a book without looking much at it, and I think that most books, they end up letting C equal 1 right away. And I've not been doing that. So, we may or may not be putting in C equals 1, except when we need it. Or if we don't. Okay, good to know. Yes.
I'm guessing it makes calculation way easier to.
Oh, a whole lot easier, yeah, that's exactly what you said, C equal 1.
But like, does it make the result correct, or do you?
Yeah, you just, it's gonna be a natural unit, so you have to restore the factor of C's that you lost.
Oh,
So you have to usually figure out how many, and again, when you do real natural units, you even let this G, so in other words, in natural units, this would become 2m over r.
oh,
Okay, so the capital G is 1 and the C is 1. And I will, eventually that C is gonna go to 1, but I'd like not to put it in for a little while. So I reserve the right to have it kind of come and kind of have it go. I'm glad I'm not taking this class. Okay, so folks, x squared plus dy squared plus dz. And that's perfectly fine in Cartesian coordinates. But we could also write that in terms of spherical coordinates. Remember when we put it in terms of spherical coordinates? So recall. In spherical coordinates. This can be written. This was written as this. And generically, how does this whole piece become? Remember, you write it like this. And then generically, what do you call all that piece here?
D omega.
D, again, it's always a capital omega squared. So this is defined to be D capital omega squared. Okay. So we have that. Okay. Now that one has spherical symmetry because it's basically the same problem as what we have over here. Okay. Now I want to make it more general. So to make it more general and still have spherical symmetry, what I'm going to do is I'm going to multiply each of these terms here by a new function that is a function of r. And to make it easier to basically calculate things with, I'm going to write all the terms as basically an exponential as a function of r. So to make this more general, meaning not flat space. Not flat space, but still static and spherically symmetric. Multiply each term by a function by a different function of R. They're going to do it like this. So that first node, remember this is e to the 2 alpha, and this alpha is a function of R. So if you look at that homework that I gave you here, for reasons I don't understand, probably because I just did it in class, this alpha here is actually a function of R. dt squared. Plus, hey, what do you think this term here is going to be? That'll go in front.
E to the 2 beta.
E to the 2 beta of R. R squared. Plus, and the next one will be e to the 2 gamma of R. D omega squared. There should be an other square in front. Okay. So the alpha var, beta var, and the gamma var are just functions of var that we haven't included they are.
Why is there an R squared in the X format?
Oh, because that shouldn't be there. But there should be a 2. Thank you. Keep me honest. I think what happened is that I have the R squared from here, and I went this lower. Okay. Now, the first thing I want to do is, this is kind of an odd thing. I want to convince you that the R doesn't necessarily have a good. Oops. Okay. So first, no. The definition of R is in the eye of the beholder. And I'm not really kidding with that. Let me explain what I mean with that. Meaning you have different values of R here. So what I'm going to do is I'm going to let R twiddle. This is the new R. Be by definition this guy up here. I'm going to take the square root of this. If I take the square root of this, this is going to be R e to the gamma of R. Okay. Now let's differentiate this with respect to, let's calculate the dr twiddle. So this is our new R. So tell me what dr twiddle is.
It's differential.
I agree. So do upper level physics majors and engineering majors. One of them.
E to the gamma of R plus
It's a differential.
The gamma R.
It's a differential. We have dr e to the gamma of R plus
The e to the gamma of R and R. Or
plus R times the partial of R, or let's say the partial of gamma with respect to R, e to the gamma of R. Okay. Or dr. Yeah. So you can pull out the dr and the e to the gamma R. Now these are 1 plus R e to the R to the R times d gamma. I can divide everything through by here and get dr. So my dr is dr twiddled over e to the gamma of R. It's 1 plus R d gamma of R. D gamma dr. I can put this all back in terms of these terms here. Then if I square this guy, I'm going to suppress the arc or the arc term here because it's just such a pain, right? And then what will I do? Well, that stuff here.
Rewrite.
Right, it is an exponential, basically a new function of twice times a new function. So I can just write this. It's basically it's to the 2r made up r to put up into here with this. This is just a new function there. And I'm back to my original expression.
What was the
Meaning that what we call r, I can always change and basically get rid of that r, get it turned as a new r. So you need a way of actually coming up with r. And so mentioned before, there was a guy called John Wheeler. He was absolutely brilliant. He actually trained Richard Feynman. He was Richard Feynman's advisor in grad school. He was also, if you watched Interstellar, he was Kip Thorne's advisor. Kip Thorne is, if you get a chance to hear Kip Thorne talk, I've heard him talk twice in grad school. He's really, really good. You listen to him talk and you go, wow, I am completely outclassed at every single level. I mean, and just he comes across as it's just incredible. Get a chance to hear him talk, just amazing. He was also I brought in that one general relativity book by Hans Ohanian. He was actually Hans's advisor. Really just he trained a number of people, just absolutely brilliant. And all of his books are not like any other books. They're always just unique. And so you have to you just can't kind of hop and skip in those books. You have to really kind of follow the narrative. But he's a really, really good writer. So this is how he suggests finding R. Is that, let's say you go to some spot here. Here's your spot. Then come out some distance. And what are you going to do? You're going to make a big circle. You're going to make a big circle. And what would you call the circumference of that? You measure that circumference. Then you're going to divide that by 2 pi, and whatever value you get, you're going to call that r. And that's r. So we'll look at this. Measuring suggests defining r as the circumference of a circle divided by 2 pi. That's how you're going to measure all the r's. Make a big circle, divide by 2 pi r. Okay. So which makes perfect sense.
How do you know what the circle is?
Oh, you just come out some distance, and what's the definition of the circle?
Equal all points.
All the points that are equal distance from some fixed point. So woo, circle. Measure that distance. Divide by 2 pi. Done. That's r. Okay.
So normal r.
Well, it appears normal.
But it's not normal.
Well, because what we're going to do is we're going to take a circle, which might have a radius 4. We're going to have an inner circle of radius 3. And so what would be the distance between the two? 1. Yeah, 4 minus 3, get 1. Turns out it's not. It's actually going to be a lot more than.
But it's what?
Exactly. Yes. Okay. Yes. Okay.
Okay.
So, because there's more space there. Which will make sense when we get that there. Okay, that makes sense. So in other words, the way I'm writing it with this, when I write this, I'm not going to put this term here. So when you look at the homework that I handed out to you, if you look at the R term, the d omega term, there's no fact of R in there, and that's why, because we're getting rid of it, because it's not necessary. Okay. So what we're gonna do is we're just gonna have a simple form. So, you know, Doctor Who or the tortoise is always, they always say speaker on the inside and the outside. After a while, when you think relativity, it kind of come away going, you know, it just might be. Maybe it is. Okay, so we will use a general metric, meaning that's spherically and static in the vacuum solution, so it's not entirely general. General metric of the form ds squared equals minus c squared. Did I put the c? I did put the c squared there. Here. We're going to use that one. Okay. Now, this is where homework 4 comes in. Hey, let's look at homework 4. My students, what will you be doing? Number 2. Hey, it looks like in question 2, it looks like in part A, you're calculating all of the sophisms. That's lucky. Hey, my class, what can you do? Once you get Christoffel symbols, what can you do? R. Which kind of R? The Riemann curvature tensors. So then you're going to find, so what you're going to do is that in homework 4, you will find, you will calculate the Christoffel symbols. And from these, then you're going to get the Riemann curvature symbols. Okay. And then from these, you're going to get the Ricci tensor. Okay. And that will be culminating here. So I'm going to actually use these results here because we're going to calculate all the other ones. Okay. You'll probably have, I'll probably give you a little push on one of these, but I want you to tinker with that yourself. When you get to these parts here, you might be a little confused on what to do. You'll look at them and say, and I'll give you a hand with that. There's going to be some tinkering with indices that you have to do. Okay. So let's proceed. So let's look at these. So that's said. So let's use our new news that you will calculate. And homework. Okay, so I think in some of this we might let t equal 1. I don't know. We're going to find out. There could be some factors of c floating around here if you put in the actual factors c's. But I listed these from the book where c was 1. Sorry about that. So look at the RTT value. RTT. And the RTT is really what one? In terms of numbers, it should be what? This would be R00. I get that one, and then RRR. RRR is what? Who says a funny joke? 1, 1. Okay, it'd be R1, R1, 1. Okay. What do you notice about them?
Quite similar.
They are. What's the only difference?
There's not the exponential to the.
Yeah, you have that stupid exponential in front of the RTT. So let's kill it and then add it to RRR. Okay, so what we're going to do, we're going to look at e to the, and I want to kill that exponential. So I'm gonna multiply this by e to the minus 2 alpha plus beta. I'm sorry, alpha minus beta RTT. Then I'm gonna add RRR. Now, what do these all have to equal? Because what do all in the vacuum solution? What do all the RRs? What does the R mu nu have to equal?
Zero.
These are all equal to 0. So if you do that, what happens? You get the following. So the exponential is killed. And I'm left with partial R of alpha. I'm going to suppress the factor of R here. It's going to be implied. Plus the partial R alpha squared minus partial R alpha partial R beta plus 2R partial R alpha here. So that's this guy. We're going to add that to the same thing. We're going to add this to this, which is almost the same thing. This whole piece here. Exactly. So what's going to happen? That fellow cancels that fellow, this fellow cancels this fellow cancels this fellow. And we're left with 2 over R partial R alpha plus 2 R partial R beta equals 0. Where this gives me partial R alpha minus partial R beta. Right. So how do we solve that? Integrate it. So we're going to integrate this. This gives me alpha equals minus beta plus a constant c. What is it in the speed of light c? This is just c. Should I call it something else? Is that fine?
Seems long, so it's fast.
Yeah.
Now, we can set. So let's see what this means here. So if I actually put this into the expression. I'm going to put that into that expression here. What does that give me? That. Which is what? Hey, what do you think I can do with time? I can rescale my time. I can let t twiddle be e to this e to the c t. Right? So that d t twiddle equals e to the c dt. And if I square it, this whole term here becomes I can do that. Okay, so I can let C be 0. This is not going to have any effect on anything. Okay. The other thing I can do is that, if R becomes really, really large. Okay, if R becomes really, really large, my space should start looking like a flat space metric. If it starts looking like a flat space metric, this exponential here should go to 1. And then this piece here needs to go away. So in that argument as well, that C here, which is not this field like here, C, that would also have to be the C that's with 0. This is a constant that always has to be 0. That's another way of looking at it, either way. So you can put that down here as well. So if you don't want to do the scaling argument. But we need this resolved. So this is alpha equals minus B. So likewise. That's not really likewise. In addition. Further. Also. If R is large. DS squared metric should reduce to the flat space metric. Meaning that this e to the minus 2 betas of R better go to 1. So the e to the minus 2c can also better go to 1. So therefore, c needs to be 0. Since c is a constant. And that would then give you, that would give, when ds squared reduces to minus c squared, reduces what we had before. Okay, that makes sense. Questions? Good. Okay, now let's look at R theta theta. It's R theta theta. Z to the minus 2 beta. R partial R beta minus partial R alpha minus 1. Plus 1 that has to equal 0. Right? So this guy here, my partial of alpha with respect to R, this has to be this guy. And that result over here. So this gives me e to the minus 2 beta times R, no, sorry, there's a 2 here. 2R partial R respect to beta here. And that has to equal minus 1. No, I don't want to do that. I don't want to do it like that. I draw that, draw. And I draw this minus 1. So I dropped this from here. So what is this? I'm going to write this in a suggestive form. I'm going to write this as 2. I'm going to write this as R. 2 partial R beta is minus 2 beta minus e to the minus 2 beta. That is minus 1. And I'm going to multiply everything through by a minus sign to make it more transparent. I'm going to write this to first and then minus Now. What's that?
Auto two.
Again, perfect. It's the derivative of what?
The R times the exponential.
This has to be e r times e to the minus 2 beta. Right, because if you take the derivative of this from here, this gives me the exponential. But then I'm going to do this from here, the r goes along for the ride. Then if I take the derivative of this, I get minus 2, the derivative of beta with respect to r, that's the exponential. So that equals 1. Hey, what can I do with that now? Integrate. Okay, can I use C or should I use that? I can call it D.
Okay.
So my E is minus 2 beta R over D. Okay. Or in other words, what? E to the 2 beta is what? I should have something else in here. Oh, yeah. Let's grow this one.
It's -1.
R plus D. Yeah. Ooh. Minus 20,000 for the compressor. That's done. Now I'm happy. Okay, so what does that mean? That means that my e to the 2 beta, the reciprocal of this is exactly what it should be. R plus D. That makes sense.
When you divide it through by R, is that turned into a 1 plus D?
Oh, I got my R here. Yeah, so when I drive through, but okay, I had my R here with this. Boy. I have to take minus 10,000 for the professor. Okay, divided through by the R. That gives me 1 plus D over R. And now I finally have the correct term. E to the 2 beta. 1 over 1 plus D over R. Right? Actually, no, I think I want to write it like the other way. We'll go back to there. So then what do we know about e to the 2 alpha here? E to the 2 alpha is e to the minus 2 beta. Right? And so what does that give me then? That gives me that e to the 2 alpha is
Just
reciprocal as the flip of that guy. And it's going to be the 1 plus d. Okay. So what does that give me? Well, if we go back to my expression here. Not better. Therefore, we can say ds squared. This is minus c squared. We have the e to the 2 alpha, but e to the 2 alpha now is this guy here. That. Okay. dt squared. Plus. Now we have the e to the 2 beta, e to the 2 beta is my friend over here. Plus in this r squared. New base. That makes sense. Now. How can I make this be recalculated? I actually look at the case where basically r is large. Okay. So if r goes to large, what should happen? I should actually recover a weak gravitational field. All right, so if r goes to something large, we should recover. Weak rotation field. All right. Which is what? Okay, remember that we have this guy here. It's going to be this minus G00. Actually, let's remember we have this guy here. If you look at this guy here, which is this gives us the G00. There's a saturation here. So what do we know about this G00? It's this guy over here. So G00. Okay, therefore, what does G have to equal then? Minus 2GM. That makes sense. Right, because we have this guy here. We're comparing to this guy. This guy here, the C squared here comes up from the C over here. So what does that give us? That gives us the final result, which is our short metric. The most famous metric in general is the Do you see anything happening out of this from here? There's one minus something. What might it be possible for this to do?
Be small.
This
R is
will
so
change.
small.
This R, what happens with this R, little r, is 2GM over C squared. If R is this right over here, what happens?
It becomes 1 minus 1 0 1 0.
So something weird's happening at that point. What happens if R is bigger than this over here? And what is this term here? That's positive. If this R is less than this value, then what is it?
Negative.
Now this becomes negative. Well, what happens over here? I get a negative, then here that's becoming positive. That's odd because what happens here is that this R here, when it's first of all, it goes to 0 basically when your R equals this value here. So something weird is happening. If your R is greater than this value, here, I'm going to call this a Schwarzchild radius, where's this? If R is greater than this value, then this term here is positive, and X just like regular distance, and time this term will negative, that X just like regular time. But if your R is less than this value, your distance here term becomes negative, but that's really what time is. And then your time piece here then becomes positive, but that's really what space does. So it's almost like when you get really, really small, your space and your time they flip. Okay. And so what's gonna happen here is that the reason we're getting this sort of behavior here is that we end up with a one. And so, now it's a matter of figuring out which way to proceed with the class. Do we do the classic cases first? Or do we go right to black holes? I'll leave it to you. Do you want to get right into black holes? Or do you want to do the classic cases for general relativity neutral? We're gonna do it all.
Let's just do the forms.
I don't know if any of it's necessary. I mean, to be honest, it's the precession of the perihelion and Mercury, that's a nasty little calculation. That's the calculation from that has some edges to it. Well, there's a couple things we have to do first of all. I want to show you how you can get gravitational time dilation from this. And we can set up a little bit about kind of I can look at some generic stuff in this first. Okay, then we can decide which route we want to go. We're gonna do it all. Okay. But run away. You know, it's real honestly not like that. Whatever. There are calculations involved. Or there are calculations. No, it's. What's the arranging? It's awesome. Okay.